Hello everyone, and welcome back. Today we're going to continue our exploration of intermediate statistics and focus on some linear algebra and matrix algebra tools that are going to be very useful once we start talking about multivariable and multivariate statistical and probability methods. So for the majority of this video, we're just going to be doing a brief rundown of some of the basics associated to matrix and vector algebra. If you do not know these things, that is perfectly okay. The intent of this video is not to have you master these materials, but more so give you an acquaintance with these procedures so that once we do get to them in the realm of statistics, you at least know or have some familiarity with their concepts, their calculations, and some of their interpretations. And of course, if you have taken a linear algebra or matrix algebra course before, then a lot of these things may be a refresher for you. So the very first thing that I want to introduce is what we refer to as column vectors. So column vectors are sort of a multi-dimensional extension of numbers. So usually we're going to be representing column vectors by letters. Some people will represent them just by letters. Some people will make them a little bit more bolder. Some people will put a little hat above them. And some people will put a little arrow in that direction. Any of these is perfectly okay, but I'm just going to be using just this basic letter representation for a column vector. So a column vector is usually going to have, say, n rows, and it's only going to have one column. So that's the number of rows, and 1 is going to be the number of columns. All right, and if that is the case, then we're going to have, for example, numbers, for example, x1, x2, down to xn. So n rows, one column, and that's what we refer to as a column vector. So the next thing that we want to sort of define on a column vector is what we refer to as the L2 norm, or just the norm of a column vector. So the norm of a column vector, which we're going to be representing by a double absolute value bar, or the norm of that vector u, is going to be defined to be equal to the square root of the sum of the squares of those components. So the first component squared plus the second component squared, all the way out to the last component squared. Now, the norm of a vector should actually look vaguely familiar to you if you're familiar with some of your basic statistical metrics. So for example, let us assume that we define the vector x to be equal to x1, x2, down to, for example, xm, and let's assume we define this one vector to be equal just a bunch of ones. Again, n rows by one column for both of them. Right? And let's assume that x bar is a scalar, or which is a fancy word of just saying a number. At least in the statistical realm. There's a little bit more one could say about scalars and vectors, but let's just leave it there. So scalar is just going to be a fancy word for number here. And let's consider the norm of the vector x minus x bar times that vector 1. So what exactly does that look like? So that's going to be equal to the norm of the vector x1, x2 down to xm minus x bar times the vector 1, 1 down to 1. So how do we do scalar multiplication by vectors? So what we're just going to do is we're going to multiply each of those components by x bar. And that's just going to be equal to x1, x2 down to xn minus x bar down to x bar. And there's going to be n of them, of course. And if you have two vectors and they have the same number of rows, in order to subtract them or add them, you just perform the operation on those particular elements. So for example, the first element is going to be x1 minus x bar, x2 minus x bar, all the way down to xn minus x bar. So those are just n numbers. So keep in mind this is still a n by 1 vector, so we're just going to sum up the squares of those components. So that's going to be equal to the square root of x1 minus x bar the quantity squared plus x2 minus x bar the quantity squared all the way down to xn minus x bar the quantity squared. So this formula should look vaguely familiar to you. For example, if we sort of put a little bracket here and we sort of divide by, for example, n minus 1, and we multiply the top by n minus 1, then what we have here is just going to be equal to the square root of n minus 1 times the square root of the sum of xk minus x bar, the quantity squared, all divided by n minus 1, which is just a fancy way of saying the standard deviation of that data set, right? So what we have here is that the norm of x minus x bar times the vector of 1s is precisely equal to the standard deviation times the square root of n minus 1. Right? So you can sort of see how this is a nicer way of representing this not so nice looking notation, right? But of course that's just a pedagogical example of linear algebra for matrices and statistics, but later on we'll get into more useful concepts. The next thing I want to introduce is the dot products between vectors. So let's assume that we have a vector, let's call it u, which is going to be the elements u1, u2, all the way down to um. And then we have another vector v, which is going to be the vector v1, v2, all the way down to vm. And we're going to define the dot product between these two vectors to be equal to u1 times v1 plus u2 times v2 all the way down to un times vm. So if you have a vector dot product with a vector, keep in mind both of these should be the same exact size, then you get a scalar. So this is just going to be a number. So the dot product between two vectors is going to be a scalar, right? Which is technically a one-by-one vector if you want to sort of think about it in that way. All right. So another important thing that you definitely should be aware of is the transpose of a vector. So the transpose of a vector. So if we have, for example, a m by 1 vector and we transpose it, so this is going to be the transposition of the vector u1, u2 down to, for example, un, what we're actually going to get, instead of an m by 1, we're actually going to have a 1 by n vector, which is called a row vector. So it's going to be u1, u2 down to um. And the reason we want to introduce the transpose is because the dot product between u and v, so this is the dot product of n by 1 and n by 1 vectors, can be equivalently represented as the transpose of u, which is going to be a 1 by n, multiplied by a vector v, which is an m by 1. And notice here that the inner dimensions n and n are both equal to each other, and the resulting scalar that we get is a 1 by 1, which is the outer dimensions. And the reason I want to point this out is when we get to multiplying by matrices, this is actually a very important thing. So therefore, u transpose v is the same thing as u dot v. So if you see one or the other, they are actually equivalent notations, provided that both u and v are both vectors with n components, which we usually just abbreviate by that notation. The next thing I want to introduce is what we refer to as numerical matrices. There are other types of matrices aside from numerical matrices, but in the realm of statistics, most of the time, matrices are just going to be a block of numbers. So a matrix is going to have m rows and n columns. So it's going to sort of look like A11, A12, all the way down to A1m, A21, A22, all the way down to A2m, all the way down to AM1, AM2, all the way down to AMN. So there's m times n number of numbers in this block, and there are several different applications in the realm of statistics where we're actually going to be using matrices. So of course, the very first thing that is sometimes complicated to evaluate is going to be multiplying matrices. Addition and subtraction are actually fairly trivial. As long as they're the same size, you just add or subtract the components. So how do you multiply matrices? So let's actually work through a numerical example just to sort of see this out. So let's assume that we want to multiply the matrices 3, 2, 1, minus 1, 2, 3, which is obviously a 2 by 3 matrix, and we're going to be multiplying this by the vector 5, 2, 4. So the first thing that you need to figure out is, can you Or is this product defined between them? So in order for multiplying matrices to be defined, the inner dimensions 3 and 3 must be equal, and the resulting matrix is going to be the outer dimensions, which is going to be a 2 by 1. So what exactly is the 2 by 1 matrix for which this is going to result in? So that's going to be 2 rows and 1 column. So that's also going to be a column vector. Let's actually give a little bit of room to write this out. So in order to find what the first element is and the second element is of this 2 by 1 vector, we're going to do the product or the dot product of 3, 2, 1 transpose times 5, 2, 4. So the dot product of 3, 2, 1 with 5, 2, 4. So it's going to be 3 times 5, which is going to be 15, plus 2 times 2, which is going to be equal to 4, plus 1 times 4, which is going to be equal to 4. Then the next element is going to be the dot product of negative 1, 2, 3 with, again, 5, 2, 4. So that's going to be minus 1 times 5, which is going to be minus 5, 2 times 2, which is going to be equal to 4, and 3 times 4, which is going to be equal to 12. So once we actually work out that algebra, we're going to have 15 plus 4 plus 4, which is going to come out to 23, and negative 5 plus 4 plus 12, which is going to come out to 11. So that is the 2 by 1 result of the product of those two matrices, which are, of course, of different size. Now, a special matrix product that is very important is when we take a matrix, which is an m by n matrix, and we multiply it by a vector, which is going to be an m by 1, and what type of matrix are we going to get when we multiply this out? Well, obviously, if those things match, which they obviously do, that means this product is defined, and a resulting matrix is going to be an m by 1 vector, right? So a resulting matrix is actually just going to be a vector. So when we multiply an m by n matrix by an m by 1 vector, we get an m by 1 vector. That is, A, which is an m by n matrix, is actually just a transformation from all n row vectors into a space of all m row vectors. So matrices are just transformations from one space to another, and there's lots of different things that you can actually do with that. So can you also do transpositions of matrices like you do with vectors? And of course you can. For example, suppose we have 3, 4, 2, negative 1, 5, 9, and suppose we transpose this. That's going to be equal to what? So the first row is going to become the first column, so 3, 4, 2, and the second row is going to be the second column, so negative 1, 5, and 9. So the transpose of a 2 by 3 is a 3 by 2. So if A is a transformation between Rn to Rm, that means the transpose of a matrix A, of course, is going to be an n by m, is going to be a transformation from Rm into Rm. Right? So this is just some of the basic principles associated to matrices and vectors, and of course there's plenty of other things that you could talk about. A couple other important things about vectors. The first one is called a unit vector. A unit vector is just a vector whose norm is equal to 1. And another relation between vectors that are actually very important are what we refer to as orthogonal vectors, and that's when the dot product between these two vectors is equal to 0. And if you have two vectors that are orthogonal to each other and the norm of u and the norm of v are both equal to 1, then these two properties together is what we refer to as orthonormal vectors. So two vectors that are orthogonal to each other and both have a norm of 1 are what we refer to as orthonormal. So if we consider the two-dimensional case of this, suppose we have some vector u which is here, and let's assume that we have another vector v that is there. If the dot product is equal to 0, either the vectors are equal to the 0 vector or the angle between them is 90 degrees. There's a theorem that sort of walks you through that, but that's pretty much what orthogonal means. It just means they're perpendicular to each other, provided that they're non-zero. And if they're unit vectors, that means we can put a circle of radius 1 and it's going to hit the endpoints of each of those vectors. There's lots of applications for orthonormal vectors, which we'll get to a little bit later. And on top of these things, let's assume that we have a matrix. So if the columns of a m by n matrix are orthonormal vectors, then A is called an orthonormal matrix. Right? And there's many applications of orthonormal matrices, which we'll definitely get to in just a moment. The next calculation on matrices that we're going to define, and this is actually only going to be defined, at least for now, for square matrices, and that's what we refer to as determinants. So determinants of square matrices. You can define determinants on non-square matrices if you're a little clever, but you lose some very interesting properties, but we're not going to get into those advanced techniques, at least today. So we're going to start off with the baby 1 by 1 matrix. So let's assume we have a 1 by 1 matrix, which is going to be equal to A. So we're going to say that the determinant of this 1 by 1 matrix is just going to be equal to the number inside that cell. So that's just a definition. The next, let's assume that we have a 2 by 2 matrix, which is going to be equal to, let's say, A, B, C, and D. So we're going to define this to be equal to the number A times D minus B times C. And if you're not sure why we want to define it this way, and keep in mind we're just going to write that as the determinant of A. There's some reasons behind it if you want to sort of have a more intuitive way of why we define that to be the case. You can visit my linear algebra series, and I go into it a little bit more detail there. So that's how you find the determinant of a 2 by 2 matrix. So let's just do a quick example here. Let's assume that we have the matrix 1, 3, 5, and 2, and we want to find the determinant of this matrix A. So that's just going to be equal to 1 times 2 minus 3 times 5. So that's going to be 2 minus 15, or that's going to be minus 13. So that's how you do the determinant of 2 by 2s. Well, if you can do the determinant of a 1 by 1 and a 2 by 2, can you do higher? Indeed you can. So the determinant of an m by n matrix can be found via this fun looking expansion, the sum from k is equal to 1 to m, of negative 1 to the power of 1 plus k times a1k times the determinant of s1k. So s1k is the submatrix of A when you remove row 1 and column K of the matrix A. So if your original matrix A was a 5 by 5, S1K is going to be a 4 by 4, at least in the initial stage of this determinant expansion. And this is not the only way you can calculate the determinant of an m by n. This is what we refer to as a first row expansion. You could actually go across any row and any column and you're going to actually get the same exact answer. If this formula scares you, that's okay. Let's go through a numerical example to sort of see how this works. So let's assume that we have the 3 by 3 matrix B, which is going to be 1, minus 3, 2, 4, minus 1, 2, negative 1, 1, and 3. And let's assume that somebody asks you to find the determinant of this matrix. So the determinant of this matrix B, so what we're going to do is we're going to be expanding across row 1. So what is that going to be? So the first element is going to be equal to 1. And notice we're at cell position column 1, row 1. So that's going to be equal to negative 1 to the power of 1 plus 1, which is going to be equal to positive. And then we're going to multiply that by the determinant of the submatrix we get when we eliminate column 1 and row 1. So that's the determinant of minus 1, 2, 1, and 3. And then we're going to be moving on to the next cell in that sequence. Then we're going to be moving over to minus 3. So we're going to have plus minus 3, and then we're going to have negative 1, first row, second column. So that's going to actually change to negative 1. And then we're going to multiply that by the determinant of what the matrix we get when we eliminate row 1, column 2. So that's going to be the determinant of 4, 2, minus 1, and 3. And then finally, we're going to move on to the next cell, which is going to be located at the 2. So it's going to be 2 times negative 1 first row, third column, and then times the determinant of the 2 by 2 matrix we get when we eliminate row 1 and column 3. So it's going to be 4 minus 1, and 1. So now that we have that expansion carried out, and we know how to define the determinants of these 2 by 2s, let's just go ahead and do that. So this is going to be equal to 1 1 times 1 times negative 3 minus 2, and then minus 3 times 4 times 3 is 12, minus negative 1 times 2 is going to be positive 2. And then we're going to have 2 times positive 1 times 4 times 1, which is going to be equal to 4 minus 1. And then this is going to be equal to minus 5 plus, and that's going to be equal to 14 times 3, that's going to be equal to 42. And then we're going to have 4 minus 1 is 3, and 3 times 2 is going to be equal to 6. And then we have 6 minus 5 is 1, plus 42 is going to be equal to 43. So 43 is the determinant of that original matrix B. You could expand across any row or any column, and you're actually going to get the same exact number for the determinant, which is actually quite interesting for those people who have not sort of explored linear algebra in grave detail before. Now, let's mention one other thing that's sort of related to determinants and their applications of them. So let's suppose that A is a square matrix, i.e. it maps Rn to Rm. So this is a fancy way of saying square matrix, n rows, n columns. And let's assume A, x is equal to y. So A is an n by n matrix, which means x and y must both be column vectors with n rows. And let's assume the determinant of A does not equal to 0. Then there exists another matrix, which we abbreviate by A minus 1 or A inverse, such that A inverse multiplied by the matrix A and A times this A inverse matrix are both be equal to this square matrix, which we represent by I, where I is the matrix with 1s down the diagonal and 0 everywhere else. So if you look at the 2 by 2 case, that's going to be equal to 1, 0, 0, 1. Right? So if that is the case, what does that have to do with this particular equation here? Well, if that is the case, then what we can do is we can multiply both sides of this equation by A inverse. So we're going to have A inverse times AX is equal to A inverse times Y. And that's just going to be equal to the identity matrix, and the identity matrix times x, one can show is actually just equal to x. So we have x is equal to A inverse y. So if you want to solve this particular equation for x, well, you can't divide by matrices in the realm of linear algebra. Long story surrounding that particular statement. But what we can do is we can multiply both sides by the inverse, provided that the inverse exists. So this exists provided that the determinant of A is not equal to 0, and there's a lot of theory behind why that is the case. One last thing associated to determinants that I want to mention actually connects back to orthonormal matrices. And I'm actually just going to state this as a theorem, and if you're from a linear algebra background, maybe you want to try and prove this. So if A, an n by n matrix, is an orthonormal matrix, then the following two properties are actually true. So what does it mean for a matrix to be orthonormal? All of the columns are unit vectors and all of the columns are pairwise orthogonal to each other. So if you take the dot product between any two different columns, you should get 0. So the first property is the determinant of A is either equal to 1 or the determinant of A is equal to minus 1. So that's a very interesting property, a very beautiful number, and there's some quick ways to figure out whether it's 1 or negative 1, but you have to know a little bit of theory about that. And one thing I haven't really shared with you, at least quite yet, and let's assume that you haven't learned how to find inverses of matrices, we haven't discussed how to find the inverse of an arbitrary square matrix that is what we call invertible, i.e. the determinant is non-zero. Well, if A is an orthonormal matrix, the inverse is actually just equal to the transpose of the matrix. So that's actually very, very nice. So if you have an orthonormal matrix and you don't know how to find the inverse, you actually do. Just take the transpose of it and you're all good. The next set of concepts that I want to explore only work for square matrices, and that is known as eigenvalues and eigenvectors. So let's start off with the assumption that A is a square and bi-n matrix, and let's assume that x and lambda are both complex vectors and scalars respectively, such that when you apply the matrix A times this vector x, you just get a scalar multiple of it. That is, if you have, for example, some matrix or some vector A, or let's call this x, for example, and you apply A to this vector, you only get, for example, a scalar multiple. Either it probably doesn't move, it gets a little bit shorter, or it just changes direction, i.e. it just stays pretty much along the same direction or its opposite. That's pretty much what this equation is saying. And if lambda is equal to 1, that means the vector doesn't change at all, and sometimes we call that a fixed point of the transformation. So if there is an x and a lambda that satisfy this particular equation, then we call x is an eigenvector of the matrix A, and lambda is its associated eigenvalue. Now, you may be wondering, well, obviously the zero vector, for example, x is equal to 0, 0, 0, always works, right? So the zero vector always is going to satisfy this particular equation. So we're going to assume that for eigenvectors, x cannot be equal to 0, right? Because zero vectors don't move at all for any matrix A for which you apply to it, right? So what we are looking for is other vectors that satisfy this particular equation. So if we look at this equation in a little bit more detail, ax is equal to lambda x, we want to find all vectors x that make this true and all vectors values lambda that are associated to it. So if we look at the equation in reverse direction, so ax minus lambda x is equal to the 0 vector, and we factor out an x out of the right hand side, we're going to have a minus lambda times the identity, because we have a matrix minus a matrix times x, is equal to the 0 vector. So we are looking to find the solution to this particular equation. So notice that x equals 0 is the only solution provided that this matrix is invertible. So there is a very special concept known as the characteristic polynomial, which is going to be the determinant of lambda I minus a. This is one definition of it. Some people will also do the determinant of a minus lambda I as the characteristic polynomial. I prefer this one for several theoretical convenience reasons, but you could do the determinant of a minus lambda I. You're going to get the same eigenvalues. Don't be scared that it might give you different answers, because it definitely won't. So I'm just going to take this as the definition of the characteristic polynomial of a, and this is going to be a polynomial of degree n of the variable lambda, right? So if we have the characteristic polynomial PA lambda, then the eigenvalues of A are the lambda such that PA of lambda is equal to 0. And you're like, well, what does that exactly mean? Let's look at a numerical example to sort of see how that works. So let's assume we have the matrix A, which is 1, 2, 0, and 3. So if you want to find the eigenvalues of this particular matrix, you need to find the characteristic polynomial first. So the characteristic polynomial of this matrix A is going to be equal to the determinant of lambda I minus A. So lambda I minus A. So that's going to be the determinant of the matrix lambda 0, 0, lambda, so it's just the identity matrix with lambdas on the diagonal, minus 1, 2, 0, and 3. So the determinant of this matrix is just going to be equal to the determinant of lambda minus 1, 2, 0, lambda minus 3. So that's just going to be equal to lambda minus 1 times lambda minus 3 minus 2 times 0, which is just going to be equal to lambda minus 1 times lambda minus 3, and you can expand that if you really want to, but I'm going to keep it in factored form. So the next thing you want to know if you want to find the eigenvalues is to set this equation equal to 0 and find all values lambda that make that true. Obviously we are going to have two eigenvalues, lambda 1 is equal to 1 and lambda 2 is equal to 3. A fun little theorem that you may already know if you did take linear algebra is the determinant of the matrix is actually just going to be equal to the product of its eigenvalues. So the product of its eigenvalues. So if we take this for example, then we have the determinant of the original matrix is just going to be equal to 1 times 3, which is equal to 3. So you can think, for example, if you have a really, really large matrix, you probably don't want to find the determinant of it. But if you know all of its eigenvalues, just multiply them together, and it's going to give you the same exact answer, which is actually pretty nice. So the next thing after you find the eigenvalues is you probably want to find the eigenvectors. So one can show, and we're going to skip some algebra here, because you're probably going to use software to solve these complicated equations anyway. So a minus lambda I. So the first eigenvalue is going to be 1. A minus 1 times the identity matrix times x is going to be equal to 0. So 1 is going to be the first eigenvalue, and we want to find the x that is associated to it, i.e. its associated eigenvector. So one can show that the solutions are going to be of the form c1 times 1, 0. So any scalar multiple of the vector 1, 0. So that's the general solution. So for every eigenvalue, there's actually infinitely many associated eigenvectors, but they're all scalar multiples of each other. So if we take, for example, the other equation, a minus 3 times I, x is equal to 0, and solve that, you can actually show that all the solutions are going to be able to form scalar multiples of the vector 1, 1. So that's going to be the general solution. And there's software that can solve those systems of equations for you, just in case you don't remember that from mathematical foundations. So to summarize, so we have lambda 1 is equal to 1, and lambda 2 is equal to 3, and we can choose, for example, the eigenvector to be equal to 1, 0, and the next vector 1, 1. So the next thing you may be wondering, well, what am I going to do with these eigenvalues and eigenvectors? So what I want to do is I'm going to put these vectors inside of a matrix. I'm going to create a new matrix U, and I'm going to have the first vector 1, 0, and the next vector 1, 1. Notice the determinant of that matrix is not equal to 0. That's actually a good thing. So if you have a bunch of eigenvectors, in particular n of them, and the determinant of the associated square matrix is not equal to 0, that means what is called an eigenvalue decomposition of A exists. So you may probably are already imagining, well, is there square matrices whose eigenvalue decomposition does not exist? Yes. But for this particular matrix, 1, 2, 0, 3, the eigenvalue decomposition of the matrix does exist. And what is it? It's going to be equal to U d U inverse, where U is going to be the matrix of those eigenvectors, 1, 0, 1, 1. Then D is going to be the matrix with those eigenvalues in the same exact order. So this is the eigenvector for 1, and then the next is associated to eigenvalue 3. And this matrix D must be a diagonal matrix. And then 1, 0, 1, 1, the inverse of that. Although we do not know the inverse of it, that is the eigenvalue decomposition. Now, some matrices do not have eigenvalue decompositions. And moreover, rectangular matrices that are not square do not have eigenvalue decompositions. But before we get into the general decompositions of all matrices, I just want to mention something very, very useful. So if A transpose is equal to A, then A is called a symmetric matrix. So if you say, for example, A is equal to 5, 3, 2, 2, and you take the transpose of that, you should be able to see that A transpose is equal to A. Therefore, A is a symmetric matrix. There's a wonderful and beautiful theorem that says this: all symmetric matrices have eigenvalue decompositions. But not all matrices are symmetric matrices. So, What are we going to do about the matrices that don't have decompositions? Like, how do you analyze them? We actually have a solution to that, and we'll get to that next. The next set of theoretical principles are actually going to come in quite handy for the next decomposition that we're going to look at. And keep in mind, not all matrices, in particular square matrices, have eigenvalue decompositions. But decompositions of matrices have so many applications in the realm of statistics, as we will see in a little bit. But these theorems are actually very, very useful. Let us assume A is an arbitrary m by n real valued matrix. You can take these things to be complex valued if you want, but most of the time in statistics we're working with real values, usually measurements from the real world. Then the matrices ATA and AAT are always square matrices. You should be able to figure out what the dimensions of ATA and AAT are on your own. And these matrices are actually always symmetric matrices. If you have some theoretical background in linear algebra, you should be able to prove that by now. Now, something that might not be super useful, or super obvious actually, ATA and AAT obviously are going to be different matrices, but they have the same non-zero eigenvalues. Generally speaking, if m is not equal to n, then ATA and AAT are going to be different sizes. But the one that is the smaller one actually has the same exact eigenvalues as the larger one, but the larger one is going to have some placeholder of zeros to sort of fill in that gap and the difference between the maximum of m and n minus the minimum of m and n. Also, if lambda is an eigenvalue of ATA or AAT, then all of the eigenvalues are always non-negative. Sometimes we refer to the matrices ATA and AAT as semi-positive definite matrices because they satisfy this inequality for their eigenvalues. Alright, now that we have those basic theoretical principles down, now let us introduce the decomposition for all matrices. So what we're going to do is we're going to assume, or we're going to suppose, that A, which is an m by n matrix, has the decomposition UDV, and let's call it UDV inverse, which sort of looks like an eigenvalue decomposition, but here we're looking at a rectangular matrix A. So what are the dimensions of these matrices U, D, and V inverse, and what is so special about them? So U is going to be an m by m matrix, so square matrix. D is going to be the same size as our A, and V is going to be an n by n matrix. Obviously, U and V should be both invertible. So both invertible square matrices, i.e. their determinant is not equal to 0. So U and V are actually going to be very special matrices. We're going to force these to be orthonormal matrices. If these are both orthonormal matrices, the inverse of V is actually just its transpose, and we can say A is equal to U d V transpose. And we call this the singular value decomposition. So the singular value decomposition of A, and one can prove that all matrices have a singular value decomposition. So what exactly are the columns in U? What exactly are the columns in V? And what exactly is located in this sort of diagonal matrix D? So U is going to contain the eigenvectors of A times A transpose. V is going to contain the eigenvectors of A transpose A. Now, how do you know that they always have, for example, m eigenvectors and n eigenvectors that force these matrices to be invertible? Well, keep in mind, all symmetric matrices, which AAT and ATA are, always have an eigenvalue decomposition. Therefore, their vectors always form a matrix that is always invertible, which is very, very nice, right? That's why I introduced that little theorem before. And one very important thing, we want these to be orthonormal matrices. So we mandate that these eigenvectors be unit vectors. So the eigenvectors must be unit vectors, and the determinant of U must be equal to the determinant of V. Right. So one very important thing about eigenvectors of symmetric matrices is they're always orthogonal vectors. We're forcing them to be unit vectors by scaling them appropriately. Therefore, U and V can be chosen to be orthonormal matrices. Therefore, the determinant of orthonormal matrices is either 1 or -1. So you need to scale them appropriately when you make them unit vectors, such that U and V both have the same exact determinant. One can't be 1 and one that cannot be -1. So that is one little caveat. So D, what is this last matrix D? D contains the square roots. Keep in mind that the eigenvalues of AAT and ATA are always non-negative, so the square root of them is not going to be complex numbers. So they're going to be the square roots of the eigenvalues of AAT or ATA. Typically, we focus on whichever one of these is smaller. So, one very important theorem that I mentioned just a brief moment ago. Eigenvectors of symmetric matrices are always orthogonal, are always pairwise orthogonal to each other. And since you can always choose those scalings, that means that SVDs for all matrices always exist. And there's several geometric interpretations of singular value decompositions, which one can explore if you want to know a little bit more about singular value decompositions, because there's definitely so many applications of that, right? Now, keep in mind, if we have an m by n matrix, and it has a singular value decomposition UDV transpose. So U, D, and V are all going to be square n by n matrices in that sense. And let's assume that we want to find the inverse of this matrix. Keep in mind, I haven't really talked about how to find inverses of matrices, unless, for example, it's an orthonormal matrix. The inverse of a square n by n matrix is also going to be an m by n, and that's going to be equal to the inverse of that matrix. Now, one interesting thing about inverses of products is that it takes the inverse of each of these, but it does them in backwards order. So we do VT inverse, D inverse, and then U inverse at the end. Now, what is the inverse of the transpose of V? Keep in mind, the transpose is equal to the inverse of V, so that's actually just going to be equal to V. And then we have the inverse of that diagonal matrix, and then we have the transpose of U. So that's actually going to be the inverse of matrix A. Now, again, how do we take the inverse of a diagonal matrix? So let's just do a brief example. If I have this matrix here, so 5 and 6, and I want to find the inverse of this matrix, this is actually just going to be equal to the reciprocals of those diagonal entries. The same trick does not work for general matrices that are not diagonal, but for this particular thing that is actually very, very useful. Right? But keep in mind something special about this D matrix. So D is containing the square root of the eigenvalues of A transpose A. This contains what we call the singular values. The singular values of the matrix A, which we usually abbreviate by sigma. So for example, if we have an n by n matrix, we're going to have, for example, sigma 1, sigma 2, all the way down to sigma m, and then zeros elsewhere. And if it's an m by n matrix, then it's sort of like a pseudo-diagonal matrix. So if you have, for example, the inverse of this n by n matrix, that's just going to be the reciprocal of the singular values. So 1 over sigma n, and then zeros elsewhere. One little calculation that's actually useful in the study of stability analysis for matrices in statistics and several other fields is what we refer to as the condition number. I'm just going to introduce it here, and you can explore what it means once we get to the applications a little bit later in multivariable statistics. And the condition number, which is usually abbreviated by kappa subscript a, is equal to the maximum singular value divided by the minimum singular value And just a rule of thumb, usually large condition number usually implies bad things when you start working for computations on matrices. Okay, so those are just some of the basics associated to singular value decompositions, which we will definitely use a lot once we get into multivariable and multivariate statistical analysis. The next operation that we're going to take a look at is what we refer to as Kronecker products. And Kronecker products are going to be very, very useful once we start hitting multivariate analysis. So let's assume that we have a m by n matrix A, and let's assume that we have another matrix B, which is a P by Q matrix. So this is probably the most general case of the two Kronecker product case that you can define. So we define the Kronecker product or denote it by this particular thing. So this is going to be a P times M by Q times N block matrix, or some people just say it's a matrix. Right, so it's just a bigger matrix. So in particular, how do we define this particular matrix? So A, Kronecker product B, is going to be equal to the jth k element of A times matrix B for each element ajk in B. So for example, if we have A11, we're going to take the element A11 and we're going to multiply that by B. Then we're going to do A12, multiply that by B. And that's going to go all the way out to A1n times B. And then we're going to continue that all the way down to, for example, AM1 multiplied by B, AM2 multiplied by B, all the way out to AMN multiplied by B. So each of those objects or cells are going to be matrices. All right, so that is just a bunch of matrices, and in particular that's a PM, so a PM by Qn supermatrix, I guess you could say. So let's do a quick numerical example just to see how to calculate a Kronecker product. So let's assume we want to find the Kronecker product of 3 minus 1, 2, 4, Kronecker product with minus 2, 3, 4, 1. Right? So obviously we have a 2 by 2 Kronecker product with a 2 by 2, so our resulting matrix is going to be a 4 by 4. So what we're going to do is we're going to take the first element, 3 of A, we're going to multiply that by the matrix minus 2, 3, 4, and 1. And then we're going to have 2 times minus 2, 3, 4, and 1. Then we're going to have minus 1 times minus 2, 3, 4, and 1. And then we're going to have 4 times minus 2, 3, 4, and 1. And this is our 4 by 4 matrix. So once we multiply all those values out, what are we going to get? We're going to have minus 6, 9, 12, 3, minus 4, 6, 8, and 2. And then 2 minus 3 minus 4, 1, minus 8, 12, and 16, 4. So that's going to be our 4 by 4 matrix. And some people will partition this out so it actually looks like a matrix with a bunch of blocks in it. There are several applications of or properties and theorems associated to Kronecker products. One of my favorites is probably the inverse of a Kronecker product matrix. So obviously this is only going to exist provided that A and B are both invertible, but in particular this is actually equal to the inverse of A Kronecker product with the inverse of B. So it actually distributes quite nicely compared to, for example, normal products AB, the inverse, that's actually just going to be B inverse times A inverse, but it distributes more nicely over Kronecker products, which is actually pretty nice. Now, in terms of the applications for statistics for Kronecker products, we'll get to them a little bit later, but I just wanted to introduce it now so that at least you know how to calculate it, just so it doesn't scare you once we get to it later on. The last thing I want to close this video off with is just a bit of calculus on basic matrices. So let's start off with the assumption that x is going to be a vector x1, x2, down to xn. So this is going to be an Rn vector, and let's also suppose that y is also a y1, y2, down to, let's assume it's ym, so it has m rows. They of course can be the same, but let's assume that they're different just to keep things as broad as possible. So once we get to some notational things in the multivariate world, we're going to assume that yk, a particular element, is actually going to be the result of some functional f applied onto, for example, xk. So for some multivariate function f. Right? Now, of course, if y and x, it's going to be a univariate function, but if I take one particular value xk, we're going to get one or possibly many values y as an output from that f. So we're just going to write this in vector form. Y is equal to f of x. That is, f is a mapping from Rn into Rm. If that's R1, that would be what we call a univariate function. Now let's introduce some of the calculus on these particular vectors that we want. So if we want to find the partial derivative of the vector y with respect to the vector x, we can write this as, for example, the partial derivative with respect to the vector x of the function f of x. So this is not x the variable, this is x the vector. So this is what we refer to as a vector derivative. So this is going to be another vector, so the derivative of a vector is a vector, and it's going to be equal to the following vector. So the partial derivative of y1 with respect to x1, then the partial derivative of y2 with respect to x1, all the way down to the partial derivative of ym with respect to x1. And then once we're done with the x1, then we're going to switch to the x2. So we're going to do the partial derivative of y1 with respect to x2, all the way down to the partial derivative of ym with respect to x2, and then we're going to continue that all the way down to the partial derivative of ym with respect to x. So that's a pretty long little vector, and in particular, that's a column vector, so I'm just going to write a little transpose above that to sort of emphasize that. So how many rows does this vector have? So this is going to be a vector with m times n rows, and of course, one column. Right? So that's how we take the derivative of a vector with respect to another vector, where y1, y2 are all, for example, functional representations of the input vector, x1 down to xn. Right? Although that might be a little bit more complicated, sometimes what we would like to do to make things a little bit more easier is to differentiate with respect to x transpose instead of x, and you actually get a nicer representation, which I'll just briefly mention here. So what will be the partial derivative of y with respect to x transpose? So this is actually going to be an m by n matrix, which is why a lot of people prefer this. This is going to be the partial derivative of y1 with respect to x1, the partial derivative of y1 with respect to x2, all the way down to the partial derivative of y1 with respect to xm, and then we're going to continue this all the way down to the partial derivative of ym with respect to x1, the partial derivative of ym with respect to x2, all the way down to the partial derivative of ym with respect to xm. Right? So this is obviously an m by n matrix, and some people will actually call this something else. Some people will abbreviate this by jx of y, which is what we refer to as the Jacobian matrix. The Jacobian matrix of y with respect to x. Right, so taking derivatives with respect to transpositions is actually a little bit more nicer if you like matrices instead of super long vectors, but to each their own. Everyone has their priorities. Now, just a couple quick derivative rules, and that pretty much covers the basics of matrix algebra for statistics, and we'll introduce the other properties as we need them when we're presenting them. So let's suppose that A is an m by n matrix. All right, so the first basic derivative rule, so the partial derivative with respect to x transpose, that's always the nicer representation of ax. You probably can guess what this is going to be. That's going to be equal to the coefficient matrix A. The partial derivative with respect to x transpose of xtx, that's almost like x squared if you sort of think about it. Keep in mind that's also the same thing as the partial derivative with respect to x transpose of the norm of x squared. And that's going to be equal to just 2 times the vector x. And one other thing I want to mention here is the partial derivative with respect to x transpose of xtax. right? Which is also the same thing as the partial derivative with respect to x transpose of the norm of ax, the quantity squared. So this is actually going to be equal to, one can prove, x transpose a plus at. And this actually only makes sense if m and n are the same, i.e. for square matrices only. So those are the basics associated to matrix algebra that you may encounter, may not, of course, depending on how deep you get into it, for both multivariable and multivariate statistics. I'll see you in the next video. Hope you enjoyed. Take care.